We're going to talk today about circular motion. So, by the end of this video, you should be able to describe why an object moving in a circle is constantly accelerating. It really is. You'll be able to figure that out and explain that in a minute. Identify centripetal forces. Don't worry, you don't know what that word means yet, but you will have that in a bit. And finally, describe what happens to the centripetal force when the mass, speed or radius of an object or the circle change. So, imagine I'm in front of you and just like this physics teacher, I've got a bung on the end of a piece of string and I'm spinning it round my head. Now ignore anything that you've heard about centrifugal forces. A centrifugal force is not a real force. We're going to talk about centripetal forces. Now in this case, we've got a resultant force. Remember, resultant just means overall force. So this resultant force is acting inwards towards the hand. The bung really wants to go flying off, and if the teacher lets go, that's what would happen. But the tension in the string is holding it in a circular path around his head. Now, if the teacher let go of the bung, it would fly off at a tangent to the circle. You can see that with this video, where a not so safety conscious person has attached a sparkler to a drill bit. Do not try this at home. So you can see that the sparks are all flying off at tangents to the circle. And now this is when the fact that velocity is a vector becomes much more important. The velocity of the bung and the sparkler is constantly changing. Now if we have a look at this diagram, this is for the bung. So the bung at the top is trying to go this way. So the velocity is in that direction. But the centripetal force, which is just the force that keeps it in the circle, the tension in the string in this case, is pulling it back towards the centre, and it keeps pulling it back so that it ends up moving in a circle. Now, that centripetal force, that force towards the centre, keeps changing the velocity, which means that the bung is accelerating. The speed isn't changing, but the direction is. The direction is constantly changing, so the velocity is constantly changing. And if you remember back from P2, acceleration is defined as the rate of change of velocity, so the bung is accelerating. So anything that's moving in a circle has a centripetal force keeping it moving in that circle. And like the tension in the string, the centripetal force always acts towards the centre of the circle. Now, the centripetal force is the resultant force that's keeping it in the circle. And if the resultant force is acting towards the centre, then the acceleration must be acting towards the centre. If you remember, F equals ma. So, why doesn't the moon fall down?
Hey Bob, I've been wondering if the Earth pulls on the moon like it seems to pull on this apple.
But then wouldn't the moon just fall down? How does it go around the Earth?
I don't know. If I throw the apple sideways, it still falls down. But at least it goes partway around the Earth. And if I throw it faster,
it goes farther. So?
If I throw it really fast, it goes really far around. What if I throw it so fast that it goes all the way around?
Do that again!
It's in orbit, just like the moon. It's always falling,
but never falls down.
I wonder if that was Newton's idea. He had powerful ideas.
So, for the moon orbiting around the Earth, or the Earth moving around the sun, the centripetal force is provided by gravity. The moon tries to keep moving in the same direction, but gravity keeps pulling it back towards the Earth, like it's constantly falling. So for the bungs spinning around the teacher's head, the centripetal force is provided by the tension in the string. For a car going round a roundabout, The centripetal force is provided by friction. You need to be able to identify centripetal forces for different situations. We'll have a look at some of those questions next lesson. Now there are three things that affect the size of that centripetal force, so how big the force needs to be to keep the object moving around in a circle. The three things are the mass of the object, and if the mass increases, the size of the force increases. The second one is the speed of the object. If you want to make it go faster, you need to have a bigger force to keep it moving in a circle. That kind of makes sense. If you tried to go around a roundabout in a car really quickly, you might not have enough friction to keep you going in that circle. And the final factor is the radius of the circle. Now, if the radius increases, the size of the force decreases. So this means that if you were to swing, or the physics teacher was to swing that bong around the head with a smaller length of string to make the string a bit shorter, you'd have to apply a bigger force to be able to keep the bong going at the same speed. And in this video, the students try changing the radius of a circle.
Okay, start.
I got it, so it's recording.
Okay, spin me. Spin me well.
Yeah. Working out much? And this goes back to the stuff that we did on the centre of mass. By moving his arm out with those weights, he's moving the centre of mass further outwards, so he's making the radius between the centre of mass and the centre of the object bigger. He's making that radius bigger, which means that he will actually slow down. And when he makes the radius smaller, he brings the centre of mass in, he'll speed up. And now you've watched and taken notes on all of that on circular motion, you can go and do the quiz. See you next lesson.